earlier it was scheduled that tours was the first DL and
Oh, okay.
along with the inauguration. So yesterday two DLs went. One was mine and other was Professor Surya's on non-volatile memory.
Mm-hmm.
So after that, one invited talk by Dr. Thirmal. So he was on this characterization methods. And
Yep.
so today morning we are starting with you, Professor.
Okay. All right. That's good. So there's
So it's an entire 4 day program, and
yeah, it's great. You see the platform. I can see people there.
yes, in the audience are there are the students. So
Yes.
it's
So
quietly
it's
packed auditorium.
yeah. Are they undergraduate students or actually postgraduate?
Undergraduate students, a mixture of first year to second year, third year, and final year.
All right. I hope my thing's not too sort of boring to them. So I try to stay on, just talk about the basics and maybe a little
Yeah,
bit.
they are quite interactive, good audience, I would say. Yeah,
Excellent. Excellent.
yes, Professor.
I'm just trying to see how can I share my screen, this one.
Yeah,
Let's
Dr.
see.
Thirmal, are you there? If you can give permissions to Professor Lan for sharing.
Yeah, I just want to check if because I don't use Google Meeting very often.
Sir, already. Sorry, we are hearing a background noise. Is that fixed?
I think it's fine now. I
Morning.
can't hear anything.
Dear Professor, good morning. Good morning, dear Professor. You can share your presentation.
I can share now. Where I can't see the share button here. Where can I find it?
No, I think you have to make Professor Lan as a co-host or give sharing activities. Even I do not see the sharing screen,
Yes,
so I think the same is with the Professor Lan.
we'll try that.
Yeah, I can't. Yeah.
Come in the front, please.
Now I can see I'm a co-host. So I'll try see if I can see the option now. Manage recording. You know which one? Is that just called sharing? I still can't see sharing thing.
Share screen in the three dots. I could see share screen as I am also made a co-host now.
I can see I can see the slot 3 dots. I couldn't see the share. Change, open, turn on, use report. There's no share option for me. I can see managing recording and streaming, but not sharing.
Dr. Thimal, can you just check what is happening? Professor Lan could not see the share screen option. Can you remove her and
Yes.
again make her a
That's
co-host?
present.
That's 1 second, sir. Please stay with us.
Sure,
One
sure.
second.
Yeah.
Hello, madam. Hello. Madam, am I audible to you?
Yeah, I can hear you.
Yeah, madam. In the bottom row, there is an arrow symbol, an arrow.
So,
Right?
You can see.
sorry.
You can click that one, madam.
So I'm putting I just turn on the more option, which is the 3 vertical dots.
Just beside that, there is an arrow, right? Arrow mark is there.
I can't hear you actually.
Yeah, there is an arrow mark is there, sir, madam. Arrow mark is there. Just beside the 3 dots.
Just beside, is that just a share? Oh, no, I got it. Sorry. I see it. It's just a present, not share. It's called present. Okay. I will try to see it now. Yeah. Okay, so here. Can you see it now? Does it?
ma'am. Yes, yes.
Yeah.
It's good. It's good. Yeah.
Yeah, it's good. It's moving. Yeah. Okay, cool. So, okay, cool. So it seems to be working now. Yep, once I turn it on, I can't see you guys, but yeah, that's not important. Oh, here. Okay.
Ma'am, I don't think in Google Meet you can present and see the Google Meet screen. So yes, you will be in your presenter mode and you cannot see the other screen.
Yeah, okay, that's fine. So
I'm
that's the
sorry
Google.
for that. Yeah, that is available in Teams and WebEx, but not in the Meet. Yeah.
In the Google ones. Okay, that's fine.
Yeah.
That's not important. So, okay, I think I figure out now. Pretty okay.
We'll take 1 minute, sir. We'll introduce the speaker today. Before that, our Ishwari madam will speak for you for what's about our nano center that we have here. Yes, madam.
Is that your? Should I start or what? Sorry.
So your voice is very feeble actually. Madam, they are going to introduce you, introduce
Yeah.
the speaker, and then you will be having your presentation.
That's good. That's what I was thinking. And I can't hear them very clearly from the on-site. I can hear you perfectly fine, but from the from the theater it seems to be a bit hard to hear.
Tamal sir, your voice is very, very feeble for both of us to hear.
Am I able to know?
Enhancing the
Hello. Am I able to listen?
A little better, but still it can be better because
Yes.
it's very, very feeble. Yeah.
Hello. Am I able to know?
It's a bit better, yes. You keep
Yes.
saying, yeah.
Yes, Professor. We are going to introduce you to the audience. Before that, our HOD madam is going to introduce our Center for Nanoscience and Technology to you, madam. Yeah.
Yeah, good morning, everybody. I think you can settle down now. This is Jayashree. I'm representing the Department of Humanities and Sciences. I'm the head of the department. And today I'm here to share, in fact, it's a pleasure for me to share about the Center for Nanoscience and Technology that is part of our department and the institute. And we have a lot of activities that are conducted through the center. Let me just brief you about the activities. We have a lot of guest lectures on updated topics. We have a lot of students working on internships, and our faculty are very active doing their research in the field of nanoscience. And we have facilities the equipment worth about 10 lakhs. This was started in the year 2016-17. And we are really happy to share that there are a lot of successes behind the center. A lot of our faculty are involved in research activities. And through this forum, I would like to encourage all of you all, because this is an interdisciplinary area of work. It is not that I am an EC student or a CSC or an EIE, I cannot work. Mechanical, automobile, all of you have a lot of scope in this area. And if you've been listening to the previous talks yesterday, I think you must be inspired. And we just hope that you will be active as a student to contribute to the society in your own way, the solutions through the nanoscience research. Okay, some brief features of the Center for Nanoscience and Technology. We have facilities, as I said, equipment worth at least 10 lakhs. The completed projects are about 52 lakhs. The ongoing projects that is part of the being conducted at the Center for Nanoscience and Technology, rupees 150 lakhs. And these are sponsored by DST and DRDO. Department of Science and Technology and Defense Research and Development Organization. We have 8 faculty who have published patents and a lot of students being very active doing their internship right from the second year. And we welcome even if the first year students would like to do a little bit of research activity at this center. Okay, a lot of activities in terms of teaching are also done. We are offering an elective, and this is being conducted, or this is part sharing with the domain faculty. So welcome you all once again, and hope you have a great day. And please be proactive in these sessions and take the benefit of these talks. I hope that this will really enrich you. Thank you.
Thank you, madam. I request now Dr. Rudramama madam to introduce Professor Lanpur to the audience.
Yes, good morning, one and all. Myself, Dr. K.S. Rudramamba, deem it as a great privilege to introduce our today's resource person, Professor Lanfu. Professor Lanfu is currently professor and head of the department Electronic Materials Engineering at Research School of Physics, Australian National University, and chief investigator, ARC Center of Excellence for Transformative Meta-Optical Systems. Professor Lanfu has been the chair of IEEE Nanotechnology Council and Regional Activities Committee, associate editor of IEEE Photonics Journal, and member of editorial board of Electronic Advances. She is deputy chair of Australian Academy of Science, National Committee of Australian Materials Research Society. Professor Lanfu has published around 200 publications, which includes 150 journal articles, 3 book chapters, 6 co-authored conference proceedings, and holds 2 US patents. Her research interests includes design, fabrication, and integration of optoelectronic devices and chemical sensor based on low-dimensional 3-5 compound semiconductor structures, including quantum wells, self-assembled quantum dots, and nanowires, grown by metal organic chemical vapor deposition. Dear Professor, we are super excited to have you here for this session and look forward to your presentation.
Thank you very much for this kind introduction. Firstly, I would like to really thank Dr. Thimo for inviting me to attending this special event, like for all about fabrication and characterization of nanomaterial, which is exactly the area that I've been working with, and also as the chair of the regional IEEE NTC Nanotechnology Council Regional Activity and Chapters Committee. I'm so excited to see that very active IEEE chapter that's working in nanotechnology and nano science area. So that's great, to see also so many students. I just talked to the Dr. Santosh. He told me that a lot of students are in the audience. So that's exactly what we want to see that's happening at local chapter level, that engagement with the young generation into nanoscience and nanotechnology. As the kind of introduction says that nanotechnology is really encompassing technology and multidisciplinary, cross-disciplinary technology that really encompasses a wide range of our field: chemistry, biology, physics, so material science. So that's really enabling a lot of new technology happening for the future. So hopefully my talk it will also give you a little bit sort of flavor how nanotechnology could be really used for different fields. So I would really start by actually acknowledge the country in Australia, where the traditional land of the traditional custodians of Australia's on which land I'm doing my presentation today, which is actually Ngambri and Ngunnawal people. So I would like to pay my respect to the elders, past, and present. So I'll start by really again to say that I'm going to talk about the nanomaterial is actually 3-5 compound semiconductor, which is a structure called nanowires. And I'm talking about a bit of how we actually make fabricating or synthesis these materials and how we actually make them into different device applications. I'm from the Department of Electronic Materials Engineering of the Research School of Physics of the Australian National University. So our group is called Nano Optoelectronic and Nanotechnology Group, and where we're actually using a specialized equipment called metal organic chemical vapor deposition system, which is actually a very commonly used CVD reactor, but it's epitaxial sort of growth crystalline material growth reactor to create 3-5 semiconductor. So this is a very important industrial sort of machine, which is able to create a lot of devices you're actually very familiar with, such as lasers, LEDs, photodetectors, solar cells. So our group, actually based on AUs, have been working with growing low-dimensional structures such as quantum wells, quantum dots, nanowires that to actually enable those kind of device applications. So you know that LEDs, photodetectors, solar cells are very traditional optoelectronic devices and very well-known application. But recently we have been also exploring using this kind of material for energy applications such as hydrogen generation or chemical sensors. I'll be touching on mainly chemical sensor and in the end of my work as well. So before I really go to talk about details, I'd like to really make sure you understand that the work I'm presenting today is really many years of research, and it's from a lot of contribution from our group members, past and present, as well as a lot of people, our collaborators, both within Australia and outside Australia. Also, our research, we can't do our research without the strong support from our facility. So we're fortunate that in our lab, we're closely, and collaborate with the Australian National Fabrication Facility and with a group of excellent processing engineers helping us with our machine and maintaining our machine, and also help us in developing a lot of various of fabrication process. And also our funding support is from Australia Research Council, and also some of the research from the Air Force American US grant. So this is outline my talk. Firstly, of course, I'd like you to really understand what we're working with. And so I will introduce you how we make our nanowires and how we synthesize and fabricate them into devices. And then I'll give you actually example based on the recent work we've developed incorporation of quantum well structure into nanowires and use that for different applications, in particular LEDs. So what is nanowires? Nanowires, from the name, that they are actually wire, wire-like structure that actually has a nano size. So that's exactly what we do. So why they're special? So because we have this nanoscale size and this unique sort of one-dimensional structure, we actually have a lot of important properties enabled by this nanostructure. So firstly is that because this is a nanostructure and it's one-dimensional structure, so when we actually grow them onto a substrate, the synthesis that on the substrate, basically because of the uniqueness of one-dimensional structure, it can relax some fundamental limitation of lattice mismatch problem when we grow a planar structure on the substrate, when we have very big lattice distance, constant difference. Thereby, because of that, it will enable us to grow a lot of more variety of material on the substrate or even on the foreign substrate. And also in terms of, creating different structures, such as this heterostructure you may have heard about, and is that you have more flexibility to grow those kind of things, right? Secondly, is that because of this nanoscale size of the material, basically it actually can have a lot of unique optical properties. More importantly, is that you can modify this localized resonance in a guided mode on this nanostructure. Then you actually change the local density of the optical states. Thereby, you can really engineer the structure of the nanowires to actually tailor the application for light absorption or light detection applications. So I'll give you some example later on that. And also, certainly, having this freestanding nanowires, you can imagine compare with a bulk structure or thin film, you will have a large surface area. So this large surface area is in particular important for sensing application or photoelectrochemical application, where you need a large interaction surface, right, with your medium. So this give us a lot of important advantage to explore both the fundamental understanding as well as application for these very exciting nanostructures. Now, largely, you probably also heard about PN junction, the diode, right, which is being used a lot for electronics as well as optoelectronics. So basically, you can imagine, because we have this one-dimensional structure, you can actually incorporate these electrical structures in both axial direction or radial direction. We call that this a two-direction, where you can really engineer your device, for instance, a carrier transporting this device and to enable new device design and new functionality and the performance. So that's the advantage offered by nanowire. That's why in the past, about 20 years also, there's a lot of research interest in this area, and people have really demonstrated a wide range of device applications based on the nanowire, including like LEDs, lasers that actually covering a broad range of wavelengths from UV to IR. And we have also demonstrated nanowire detectors from UV all the way to terahertz range, nanowire solar cells with very high efficiency. And also, Professor Pei Dongyang's very early on, 2010, has already imagined, provide this visionary sort of nanowire-based optoelectronics. And because of the nanowires, while the small size, the high performance, low cost, you can really make this very highly integrated optoelectronic circuits, where you can integrate, solar cells, sensors, photo lasers and waveguides and photo detectors, everything onto the same chip. And there are some basic nanowire circuits being also demonstrated. But we all know that, nowadays, we're not only interested in the individual components, lasers, LEDs, and all this. We also want to have integrated optoelectronic system where we can have a fast data transformation, such as optical interconnects. We want to have LiDAR, which will be used for a range of applications, such as remote sensing, autonomous vehicle, the smartphone, iPhone 12, you have the LiDAR scanner, which you can explore your environment more more clearly. So those kind of application, AR, VR, hologram for education, for medical applications, and that's why those systems actually require this very highly integrated functional components that's all into the small area, right? And that's why Facebook has actually renamed themselves as a Metaverse, where that's really because we all want to use in this metaverse. What we want to use is use light to generate and manipulate and detect them in efficient and faster and more functional way. So if we look at how we actually make 3.5 or compound semiconductor nanowires that we use in this two type of technique. One is called bottom-up technique. The bottom-up technique, there are also two different ways. The first way is called we're using some little nanoparticles such as gold. We spray them onto the substrate of your semiconductor. It can be a gallium arsenide or indium phosphide substrate or even silicon substrate, right? That's the most early study. And using this gold nanoparticle as a little seed to actually grow nanowires, because they can become the little sink to absorb all the gas phase precursors to interact with and to dissolve into that and promote this one-dimensional one-dimensional growth. And also you can use some nanolithography to pattern your substrate to make a gold nano disc and then use that to grow nanowires. And thereby you can grow this very nice and regular array. On the other hand, we can also use another technique, a more template-based technique, where we don't have to use the metal nanoparticle, because metal nanoparticle could sometimes introduce contamination into the in your system, which is not favorable for device applications. And also, you have some limitation in terms of dopant incorporation, or you have also problem of growing larger size nanowires. So there's some issues, limitations over there. So there's a sort of alternative way to making them is to actually cover your substrate, semiconductor substrate, using a thin layer of oxide, such as silicon dioxide, and then you're using nanolithography to define the position of the nanowires, and then you etching using using dry etching or chemical etching to actually open up holes there, and then you put this one into the MOCVD reactor to grow nanowires. So this way you avoid incorporation or using of the metal nanoparticles. Those is using a reversed way, we also can do the top-down etching. And then that one, you don't need to have an MOCVD reactor, which is actually quite expensive, piece of equipment, millions of dollars. So that one you can using a simple ICP, inductively coupled plasma etching technique to etching nanowires. In this way, you can also have some application of, certainly, we know that doing top-down etching, you will inevitably introduce some surface damage. So those surface damage could be problematic for a lot of optoelectronic devices, such as lasers or solar cell. However, it can be used for other applications, such as sensors, which I hopefully will have time to give you a little example later on as well. So we're really looking at understand different fabrication technique or synthesis technique to making nanowire first, and then we're actually using that to find the appropriate applications, right? That's what we do. So once we have a nice nanowires array fabricated, so one thing I have to actually mention is that because if you're using this whereas spraying things randomly, of course you will have a lot of non-uniform nanowire growth, because when you grow your nanowires, and then when you have the precursors, your atoms coming down, because of this non-uniform dispersion of your metal particles, they're not very, you won't be able to control their position. Thereby, your nanowire material will not be very, after growth will not be uniform in terms of height, diameter, and the spacing. So using this, more spacing, positional controlled way by doing nanolithography, they will actually grow this highly ordered or fabricate this highly ordered nanowire array. Thereby, you can actually have more ability to design the optical property and electrical property. So that's the approach we're actually taking. So here's an example. Once you have nanowire grow, because they are so tiny, right? You need to imagine those images taken under the electron microscope. It's not a normal optical microscope, because they are in nanometer size. You can see this 500 nanometer scale bar. So this is image taken under the scanning electron microscope, where you can really see nanometer size, like down to about 1 or 2 nanometers, right? So that's why we can see them. But in normal things, if you have I have a sample show you, I have thousands of nanowires on the substrate, you won't be able to see it very clearly, because they're just so tiny. Because they're so tiny, so they have very small mechanical sort of, very fragile. So it's very easy to knock them down and transfer them to the other substrate. So if you use a piece of paper and gently knock down, cut it with a sharp tip, gently touch those nanowire array, you actually be able to actually transfer them onto a substrate to make a single nanowire device. So we're actually doing that. So this is one of the example of this single nanowire device we're fabricating in our lab, where it's a LED, I believe. So if it's actually single nanowire LED device. So what we do is we transfer that to the substrate and contact them, making gold contact on end through the nanolithography technique, and then we do measurement. So this is a single nanowire device. We can also make them as assembled array device. So what we do then is actually trying to infiltrate them with some polymers so that we can enhance their mechanical stability. And then after that, we can do some etching to expose the tip of the nanowires, and then we can make some metal contact either on the top next to a nanowire array or on the bottom. Thereby, we can make them into a variety of devices, including laser, LED detector, solar cell, and chemical resistive sensor, which I'm going to talk about today. So in our group, we've demonstrated a lot of single nanowire device in the past, and as well as array device. So I wouldn't have time to really talk about each single of them. Basically, what I want to show you is that there's a lot of possibilities of exploring this unique property of these nanostructures, right? You can see that by changing the materials as well as the characterization technique, we actually have demonstrated that single gallium arsenide and antimonide nanowire, because they have actually a lower band gap, we're able to actually measure, achieve the photo detection at telecommunication wavelengths, which is 1.3, 1.55 micron, and at room temperature, right? And if we're actually making some making some gallium arsenide, aluminum gallium arsenide single nanowire, we actually can make them as a photoconductive terahertz detector, where to detect some really narrowed, terahertz response because of the, the fast nature of large surface due to the large surface area of material, and the fast response carrier decay can be achieved. So we can actually make them as a photoconductive terahertz detector. We also have shown that if we can design nanowire array with different thickness, diameter, we can actually change the resonance of the whole nanowire array. The absorption will change, and thereby we can achieve this multi-wavelength, photo detector ranging from 500 nanometers all the way to 900 nanometer photo detection. So we grow all this different nanowire array with different diameter. We can achieve this multi-wavelength detector. We have also done top-down etching the nanowire by actually etching the indium phosphide substrate and then contact that and wrapping that with some zinc oxide material, which is, we know, large band gap, but they form some nice type 2 band alignment with indium phosphide. So it's a hetero junction. Thereby we can use that to achieve a radio junction based nanowire solar cell with quite good efficiency and performance. So that's what we have demonstrated. Using a similar structure, we also demonstrate that they're highly sensitive, self-powered photo detector work under, they'll be able to detect single photon level of photo response. So it's a lot of opportunity using top-down as well. Again, we've also demonstrated like making them using top-down etched indium phosphide to make them a chemi-resistive sensor, which is highly, sensitive for nitrogen dioxide nitrogen dioxide gas sensing, which is nitrogen dioxide we know is a very well-known air pollutant that coming from your car, your petrol-based car. So, and I know that in India there are lots of cars on the street. So the pollution is a problem. So those kind of nanowire array can be really, really sensitive to measure those kind of low-level, high-level, of nitrogen dioxide concentration. It's actually in the air. So it's a lot of opportunities over there. So now I'm going to talk about a bit more focus on indium phosphide nanowires, which is actually the material we actually do a lot of research in our lab. So as I said, we normally grow them by using epitaxial growth technique, but the epitaxial technique we use is the selective area epitaxial, where we're using a thin layer of dielectric as a template to create a nanowire array with well-designed diameter and spacing. And then we put it into this MOCVD reactor. We pass on the group 3 and the group 5 precursors. So for indium phosphide will be trimethyl indium, and for indium, and for the phosphide we're actually using some phosphine gas to put it in. Thereby they provide this gas precursor, and on the high temperature we heat the reactor onto high temperature. Thereby we can decompose these 2 different precursors, provide group 3 indium and phosphine, where the epitaxially grow on your substrate. So that's the whole process. Of course, we need to optimize our growth parameters, very important parameters. So growth temperature, the gas flow rate, and group 5 and group 3 precursor ratio, because that will determine the how good the crystalline material you are, as you will see later on. So after, of course, optimizing this, we're able to grow a really wide range of indium phosphide nanowire array with different diameter. So remember, we can really open different holes onto the substrate, thereby we can control their diameter. And we can see that if we do structure analysis using transmission electron microscopy, we can really see the lattice alignment of our nanowire. We found there a Wuzite, beautiful hexagonal Wuzite-based indium phosphide nanowire without any stacking force. This just demonstrating the high crystalline structure of the material. And then we, of course, need to do some optical electrical measurement to evaluate the optical electrical properties. So we do some time-resolved photoluminescence measurement. So basically using a laser to pump your material to create electron hole pairs and then measure the recombination emission from those nanowires. So by doing this measurement, you're able to really, from the the shape of the intensity of the light luminescence from your material, and from if you measure also the line width, you really can tell if the material has a good quality. If we do a time-resolved photoluminescence, you can really evaluate carrier lifetime, which is very important. Again, measurement for the material, because carrier lifetime it tells you longer lifetime means like smaller, less defects in your material, right? So this range of measurement we have to. We also measured with our collaborator in Oxford. We measured optical pump terahertz probe spectroscopy, and then we can actually generate to also evaluate the mobility of the material, because you know that mobility is also important with. For semiconductors, the higher mobility, the better, the faster the carrier transport on the electric field, and then you get, better transport performance. So all this we've done, and then we actually find that our indium phosphide nanowires grown by selective area epitaxy have very nice, compared to other, growth, compared the real S growth material, we can see that they have very low surface recombination velocity, has a very high mobility, and has a very long carrier lifetime. So all this indicate a good material quality, which you can use it for device application. Okay, so again, I would like to demonstrate a few, indium phosphide nanowires, single nanowire device that, based on the selective area epitaxy, because I'm going to later on talk about, array device, but I would say single nanowire device is a good platform to study some fundamental properties of the material, because you avoid this group effect, right? You can imagine in an array of nanowires, we will have thousands of these single nanowires, and if you have some non-uniformity with the growth, you have or fabrication, or if you have problem with your fabrication of the whole device, you will have a lot of complex issue to interpret the results. But whereas if we have actually a single device, you can really see some interesting effect directly. So we have actually over the past, demonstrate single nanowire based lasers. So you can see the lasing from this single wire. We have also demonstrated broadband terahertz response from those single nanowire detector. And certainly later on, we have fabricated a crossed nanowire based terahertz detector. So using 4 crossed nanowire, this is just basically enhanced the signal. So we have making this crossed nanowire networks, which are able to actually measure the polarization state of the incident terahertz radiation, because you can using this tool forming a polarization sensitive channel and to measure the polarization states of the nanowire. So this is the interesting work coming from a single indium phosphide nanowire. And certainly during the growth of the indium phosphide, we can actually introduce different doping, right? So silicon and zinc create the N-type and P-type doping during the indium phosphide growth, and then we can contact them making to a single nanowire solar cell. And you can see this is the electron beam induced current, which reflect your built-in electric field of the nanowire. You can see this contrast, EB current contrast from the measurement, and showing that we have achieved a built-in electric field in single nanowire. And by actually designing this, the length of the field and all this, we actually can enhance the solar cell performance. So we have got for a few publications in this area, and if you're interested, feel free to have a look. Then I want to talk about one fancy structure you probably all learned in your quantum mechanics about quantum wells. So quantum wells is a very important quantum mechanic sort of structure where you learn about all this, carrier confinement and quantization effect of the energy states, right? So you've learned all this, but in particular for semiconductor. So in theoretically, quantum well is just it's a potential well that for carriers such as electrons, right, that you can confine them inside this potential well. But experimentally, how can you actually implement or achieve a quantum well in semiconductors? So in the semiconductor, quantum well is actually quite easy to achieve. It's just called a heterostructure. Basically, it's a structure made from different materials. So how we form that is we actually normally sandwich a thin layer of small bandgap semiconductor with 2 layers of large bandgap semiconductor material. So put it this way, gallium arsenide is a typical 3,5 semiconductor, has bandgaps about 1.42 electron volts. And if you put aluminum inside, you actually can increase the bandgap quite largely. So thereby, if you're using epitextual growth technique, we can grow, L gas, gallium arsenide, and L gas. So along the growth direction, you can actually form. You can see the energy band between gallium arsenide and L gas are different. Thereby, you create energy sort of bandgap discontinuity here, and then you actually create a potential well in the gallium arsenide layer. Thereby, all the carriers actually like to fall into the energies in the energy levels in the gallium arsenide. So if you actually grow this gallium arsenide ultra thin to few nanometer thickness, the quantum confinement effect will be enabled. So in this case, then the energy states in the conduction band and valence band becomes quantized, and your electrons, the holes, will actually be sitting on this quantized level instead of continuous level. So because of this quantization effect, we call it quantum confinement effect, right? You will have very large, recombination efficiency because your carriers being really confined in state in the discrete level instead of continuous states. So the wave function of the electron holes becomes better overlapped, and then you have a higher recombination efficiency. So this has been widely used for device applications. And also you can imagine if we change the thickness of your quantum well material or composition of the quantum well material, you actually can change the energy levels, right? In this way, you actually can engineer the bandgap of the material and thereby to engineer the wavelengths of your devices. So because of this, the invention of and realization of quantum world actually leading to real very fast advancement of the field of optoelectronics. And that's why the Nobel Prize 2000 in physics being awarded to these 2 gentlemen who actually developing semiconductor heterostructure and using for high speed and optoelectronics, and they actually sharing this Nobel Prize with Jack Kilby, who is actually inventor for integrated electronic circuits. So it's you see in optoelectronics, electronics, it's very important in the field, and integration is also very important. So quantum wells being used for a lot of the optoelectronics, as I mentioned, for lasers, LEDs, because of quantum confinement effect, you can reduce lasing threshold, and enhance also tune the emission wavelengths, and also actually by putting quantum wells into a triple junction recently, a record efficiency solar cells has been also achieved. And also, if we actually look at the transition absorption within the conduction band, we call it inter-subband transition, because this inter-subband energy levels has quite low energy. Thereby, you can use that for mid to long wavelengths quantum well infrared photodetector applications. So you can really measure the low energy photons for thermal imaging applications. So the very well-known application for quantum wells. And if you look at, all these things are very great. In the past, people do a lot of application, using quantum wells in devices. So what we want to do is say, how can we implement them into the nanowires and then use that for different applications? So why we want to do that in the nanowires? Because we know that in the planar device, such as LED device, we'll have, you know, the one due to the internal quantum, the internal reflection effect, the light extraction from a planar structure is actually limited. So if you have a quantum well inside a LED structure to enhance the efficiency, they can be very efficient, emit light. But however, because of this planar structure, the light is very hard to escape. So normally, light extraction efficiency from LED is very poor, like 10% or something. But if we have a nanowire, we have a lot of space here, right? So the light extraction efficiency can be tuned by changing the spacing of the nanowires, as well as their diameters. So in that case, we basically, by changing the design of the nanowire array, we can really tune the efficiency, light extraction efficiency effectively. So in fact, we've done some basic simulation which shown that in a properly fabricated and designed nanowire array, we can achieve 70% of light extraction efficiency. Also, as I said, if we implement quantum well inside of a nanowire array, we can also have the quantum confinement effect and also bandgap engineering, which will be also very important, right? So what the quantum well system we want to do is indium gallium arsenide, indium phosphide, which basically can offer the telecommunication wavelengths for very well-known, you know, quantum well structure offering telecommunication wavelengths were used for fiber optics. So that's the important material to study with. That's why we use indium gallium arsenide, indium phosphide. And of course, you will say, okay, so wavelengths is 1.5. They're good for telecommunication, but they are, you can't see it. We're very familiar with the LED that you can see, visible LED, the blue, the green, the red, right? So why we want to do infrared? Apart from fiber optics, also you can see infrared LED even based on, you know, near infrared, like 800, 900 nanometers. They have a large market. They've been widely used for biometrics, the imaging, lighting, surveillance, you know, applications. And in the you know, currently, you know, there's a lot of emerging technology like Li-Fi holography, and we actually, people actually also looking at using infrared LED. So they have a lot of, you know, important application in addition to telecom. That's why we are interested to do that. So I've mentioned before that we have using, you know, selective area epitaxy to develop this very nice, beautiful bullseye-based indium phosphide nanowire array, as you can see here, right? That's what our work. So what we want to do is introduce a thin layer of indium gallium arsenide, which will be the quantum well material, because indium gallium arsenide has a smaller bandgap than indium phosphide. So what we do is like we grow. What we want to do is like when we're doing emulsivity growth, we'll grow you know, a thin. A short, you know, indium phosphide substrate nanowires, use it as a little base, and then we can switch in the precursors for indium gallium arsenide growth, and then for very short time, a few seconds, because we want a thin layer. Remember, thin layer of quantum well, right? And then we keep going, switch off the, you know, for instance, the gallium source, and switch back indium, switch back with phosphine. Thereby we can grow indium phosphide. So by doing switching back and forth different precursors, we're basically able to grow, you know, quantum wells with barriers, multiple quantum wells with multiple barriers, such as the example given here, right? InGas, this is 5 InGas quantum well growing here with indium phosphide barrier here. And if you look at the bandgap structures like that, right? You have InGas, you have indium phosphide. That's the, you know, bandgap, simplified bandgap structure for InGas quantum well. It's very easy saying, you know, just by switching off inside a few seconds indium gallium arsenide, just grow one thing by incorporating one thin layer of indium gallium arsenide. What you see is this change of morphology. I still hope you remember that beautiful hexagonal shaped indium phosphide nanowire array I showed you just, you know, a few slides ago. And then this SEMP picture showing like when we put just a few seconds of InGas growth, the morphology of a nanowire becomes like that. And then if you look at the cross-section view of the TEM, you can actually see this thin layer of indium gallium arsenide quantum well formed inside the nanowire. because we can confirm that by doing some compositional analysis using EDX mapping inside TEM. You can see that, with different composition of the quantum wells, and you can see that the quantum wells actually, in terms of composition, quite non-uniform, and also we have quite a different components. We have this actual component, we have the radio component, we have a corner component that's reflecting over here. Of course, you can do the structure analysis. And what we found is that our woodside-based indium phosphide, after growth, it have an actually complex structure. However, the main message here is that the quantum well, which is here, is actually zinc blend based. So basically, we transform our growth of InGas. When we grow indium gallium arsenide material, that layer actually becomes zinc blend, which is actually, zinc blend is a cubic lattice. And if you look at woodside, it's a hexagonal lattice. So they're very different crystalline structures there. So what's the reason? Of course, we've done a lot of analysis and understanding TM analysis. I'm not going to go to detail by just saying, because this nanowire formation is very complex. So we need to think about thermodynamic process, and the surface energy plays a very important role, because nanowire have multiple faceting. So the growth, the surface energy for the growth are very different. Thereby, that's actually leading to this non-uniform growth at different surface when we introduce indium gallium arsenide. And then that's introducing all this very complex morphology evolution. So that's what we've seen. But still, how about the optical property? Though we know the structurally there's some transformation, but how about the structure? So if we do a position-dependent photoluminescence, look at the light emitted from those nanowires, we found that they have a position-dependent emission. As you can see here, when we move the position of excitation of the laser from top to the bottom, you can see the involve the change of the luminescence spectral from a very sharp peak at short wavelengths and go to quite a broad peak, multi-component peak at when we move to the bottom of the nanowire. So that means, like, really we have on the top, we only have, the actual quantum well start contributing to the emission. And when you move to along towards the bottom of the nanowire, and the radio components start to play a role. So you see the rising of the radio quantum well component. So that's very consistent with the TM results. So the optical property looks pretty good. The PLS actually is quite bright. So what we did next is we're trying to see, okay, we have a quantum well, how about making them into a device? So let's put in some doping. So we're putting some doping when we do the growth, so we'll create this radio PN junction. So we know that when we have a PN junction, if we positive bias it, we inject carrier inside. So with the help of the quantum well, the carrier will be efficiently injected into depletion or region of the this PN diode, and then they will recombine in the quantum well and give out light. So we've indeed make a fabrication of this single nanowire device. So what we do is that we have to, do photolithography electron beam lithography, so which is basically high resolution lithography technique, so that we can actually cover half of the quantum nanowire, so that we can do some etching. Thereby, we can really contact the P core, P-type indium phosphide core on this side. And then we actually release that, and then to do some etching. And then after etching, we could actually do photolithography for contacting, thereby etch the P-type core and N-type shell be simultaneously contacted. So by doing that way, we can inject current and measure this nice, turn on of this diode, IV characteristics. And if you look at the electroluminescence, by injecting current, we can see this enhanced luminescence as a function of the current injection, which really showing that we have got a good sort of LED device coming from this tiny little nanowire, which is only a few micron in length and 300 nanometer also in diameter. Of course, we know that, as I mentioned, light extraction is one of the things quite important. We would like to use the nanowire array to achieve good light extraction. So we know that our nanowire have a very the complex morphology, right? Look at that inclined facet, and if you look at the top, they're actually triangular shape, and bottom hexagonal shape. So we've done a lot of simulation and trying to understand how the light absorption properties in this kind of nanowire shape and how the light extraction will be affected by shapes. So I'm not going to the details of the simulation, rather than just saying like we actually do say that if we have this inclined facet, non-uniform morphology, the light extraction on the top triangular is actually quite low. But if we have rather uniform morphology, even this triangular shape, it has actually quite nice, you have probably about, double that light extraction. And this is because this inclined facet basically causes disruption of the optical resonance that leads to some optical loss. That's the reason. So my students thinking about understanding the growth, so he actually introduced us the actual step during his nanowire growth, basically changing the surface energy of the nanowire. And thereby he's able to actually grow much uniform nanowire from this quite non-uniform morphology into this predominantly triangular triangular top and uniform nanowire array. You can see the enhanced the diameter as well as the length uniformity. So after that, he said, okay, I'm pretty ready for making them into array device. So what we do is that we planarize the sample and making contacts on top and the bottom of the nanowire array, and thereby we can inject current. So you can see this bright light coming from the nanowire array. And this is infrared light. And of course, you can see that we have a quite nice light coming from this the whole array, which is about 200 micron by 200 micron in area. Of course, we're not stopping there, because if we're carefully looking at the simulation results again, like if we look at comparing the light extraction from the top triangular shape and the bottom hexagonal shape, we found that certainly hexagonal shape, some facet somehow help the light extraction. Then it's quite ideally to make hexagonal shaped nanowire. So that's what we want to do next. So how have we really transformed that triangular facet into a hexagonal facet? So we look at the literature. So what we found is that by changing the growth window, actually people can making woodside faceted nanowires and mixed woodside zinc blend faceted nanowire. And from previous study, we know that if we actually can create a zinc blend facet in the nanowires, that might be able to actually more enhance and enable the zinc blend follow-up zinc blend in indium gallium arsenide growth. So that's our sort of thoughts behind that. And indeed, literature actually supporting that, saying that if you actually change your growth window by growing nanowire at lower temperature and higher 5/3 ratio, you actually can rotate this hexagonal shape 30 degrees. So you can put in some attention to that. You can see that with the same alignment, you actually can rotate a nanowire facet by 30 degrees, just changing the growth temperature. So my students start really looking at the mixed phase zinc blend sort of dominant in the nanowire growth by changing growth temperature, and also 5/3 ratio. You can see the optimization of the shape as well as the morphology of the nanowire. So we can achieve this optimized through growth condition from previous woodside-based nanowire growth. And if we do the analysis, so we do have quite a lot of zinc blend segment being incorporated. So you can see that the blue color is zinc blend and then some transition sort of area. And if you look at the photoluminescence, we do see, like, in addition to the woodside peak before, we have actually a zinc blend peak. So that's really demonstrating using this technique, we're able to actually grow, and the carrier has very good lifetime, indicating good optical property. And by implement this new growth, method of changing growth window, we actually can demonstrate, not only one quantum well with good performance, we actually morphology, we can actually demonstrate 5 quantum well or even 40 quantum well with good morphology, as you can see over there. And then if you look at the cathode luminescence, light emission from the nanowires, they're very uniform, right? So that's meaning like we can really make use of those kind of nanowire for device application. So again, this is the transmission electron microscopy, really saying that highly uniform, quantum well morphology is formed all the way from top to the end. Nice image. So if we, with this beautiful, radio quantum well and also uniform quantum well grown, if we pump them hard enough, we actually can achieve room temperature lasing from the quantum wells. So you can see this 1.3 micron emission lasing from our quantum well, showing the good material quality. And then, of course, we said we want to make them as LED. How do they look? So this is hexagonal, faceted into that. So we actually implement the doping into the one quantum well structure to actually look at their LED performance. So this is just some mapping showing that our quantum well structure form inside this structure. And we understand their spectral luminescence property from radio and actual quantum wells. So now we look at the LED. So we fabricate them into the LED device by, contacting the top of the, the ITO layer. Basically, it's a transmission parent, oxide layer, conductive layer, to contact our LED. And then we inject, current at different bias voltage. You can see at different bias voltage, you have the light will become brighter and brighter from this nanowire array. And if you look at LI curve, in particular, pay attention to the power. So this is a 16. Now we can get, for this particular device, we can turn on at 2 volts, and we have a large 16 micro electron volts coming from, microvolts coming from our nanowire array. This compared to the previous triangular faceted nanowire, which is we can only achieve about what is that value? Yes, about 3-4 volts from there. We have actually much larger enhancement of the power from our modified hexagonal based nanowire. And this is the electron luminescence, again showing that we have a very nice broad electron luminescence up to 1.6 micron, and the wavelengths can be actually tuned by tuning voltage from 1.5 volts to 12 volts. And this can be also modulated quite fast at the gigahertz level, which is very useful for optical communication applications. And furthermore, we can have more tuning of the wavelengths of the LED by growing nanowire array with different pitch size. So if we change the pitch of the nanowire array design from 0.8 micron all the way to 2 micron, we can achieve a large tunability of the wavelengths from 1.5 to 1.75. To up to 2 micron, more than 2 micron. Tunability will be very useful for multi-wavelength light source application. So this is also quite important. And of course, if we actually design the nanowire array into very small sort of area, so this one you can really reflect, you can see there's just each line will have just a few nanowires. We're still able to get them actually emitting quite nicely. So this is our ANU, Australian National University logo. We can see that made from the LED. So we think this is very promising for the nanowire array, very promising for the multi-wavelengths, multi-pixel, individual addressable nanowire LED array at a very low power consumption in the future. So we're not really satisfied just only there, because as I mentioned, we make nanowire growth based on the Wu-Zai zinc blend sort of phase in mixed phase, enable us to achieve very uniform quantum well growth. But one of the issue with that growth is that when we introduce that growth recipe, which from the beginning start from very low temperature, high 5/3 ratio. The problem is that recipe actually promoting a lot of lateral growth. So basically, enable nanowire grow in the radial direction rather than the actual direction, length direction. A limitation to that, we can only grow very short quantum wells. So they're fine, short nanowire. Short nanowire is fine for some application. But for other application where we actually want to have longer nanowire with larger active volume, as well as have controlled design of the nanowire sort of structure or optical cavity, we want to have the flexibility to grow nanowire with controlled length and diameter. So how can we do that? So my student also again think of another way by growing Wu-Zai based core only indium phosphide. Go back to indium phosphide Wu-Zai base. And then we promote a core shell structure after that by introducing our sort of low temperature, high 5/3 ratio to rotate the facet and somehow actually follow up the bullseye structure of indium phosphide base, because we're not introducing indium gallium arsenide there yet. But by doing that, we actually, remember we said, you know, when we adopting this low temperature recipe, we actually rotate the facet. You can see the rotation of the facet here as well as here, right? So when we're rotating the facet, we enable actually the energy of the facet favorable to formation of zinc blende indium gallium arsenide. So that's a very important, again, crystal facet engineering for our nanowire growth. So this is just showing like when we do this recipe, we still can grow very good quality nanowire with this core shell sort of structure and good rotation facet. Based on the recipe, we can now introduce indium gallium arsenide again, which turns out to be quite uniform and also with good dimensions. So we can actually control them to grow longer nanowire in this way. So this one, we actually pump them harder. We pump them using light laser. We actually can achieve, you know, room temperature lasing, very beautiful lasing at also 1.55-ish micron. So this is coming from our core shell-based substrate indium phosphide and then grow indium gallium arsenide. So I'm pretty running out of time. Basically, I just want to show that also by incorporating quantum wells inside of nanowires, you can also use them for photodetector. So remember, when we put quantum wells inside, we basically achieve a different band gap compared to your host material indium phosphide here, right? So by doing that, we can really extend the absorption and then the detection wavelengths to longer wavelengths. So we can really extend from around 950 nanometer for indium phosphide absorption all the way to actually 1.6 micron for indium gallium arsenide. In this way, we actually can grow, you know, achieve this very important detection wavelengths for photodetector. And then because this unique radio transport, you remember because our quantum wells are radio, dominated the radio component. And if you actually apply bias to collect your carrier, photo-generated carrier, because of the radio morphology, but carrier path, we actually can achieve very fast collection, efficient collection. Also, you might also achieve some optical gain inside this transition process. Thereby, we can achieve the high responsivity of the detector at both 980 nanometer as well as 1550 nanometer wavelengths, which is very useful for a lot of applications. And finally, just want to touch down is that I mentioned that once you have quantum well inside nanowires, you can also employ this inter-subband transition within conduction band. The advantage of that is that you can really because the energy levels between this inter-subband compared to band-to-band transitions much smaller, you can use them for mid-infrared to long-infrared photodetection, which is very useful. However, from quantum mechanics, we know that this inter-subband transition will not be happening for this normal incident light. So if you have a planar structure growing planar quantum wells, normal incident light cannot be absorbed. So normal in this kind of detector, QUIP, we call it, using the inter-subband transition, we have to create this grating structure on the surface to enhance light scattering and then to actually achieve this this photodetector. However, in a nanowire, it's different because we create this radial sort of wrapping quantum wells, and what happened is that the light absorption coming into this one, you actually naturally can absorb this inter-subband. You can naturally absorb this normal incident light, and thereby it will have a lot of simplicity for fabrication. At the same time, because we're using nanowire, we actually reduce the amount of material by enhance the large sort of 3D volume. Thereby, we actually can leading to low dark current without sacrificing your active region volume. So all this offer you advantage for QUIP application. In fact, I haven't included the results. We have recently demonstrated that our quantum wells are able to achieve mid-infrared photo detection for 4 micron wavelengths. Okay, so I just want to quickly conclude my talk. I hope through my talk, I gave you this a bit of basic understanding how we actually can fabricate synthesis, nanowire, and the devices, which actually can be used for a lot of, interesting device applications such as LEDs, laser photodetectors, solar cells, and as well as the photodetectors. I didn't have the time to talk about sensors, but I'm saying that actually they can be used also for very sensitive chemical-resistive sensor, which demonstrate both acetone sensing, which is very important for type 1 diabetes, as well as nitrogen dioxide sensing, which is actually for the air pollutant, which I don't have time to talk about that, but you're most welcome to look at our publications on this area. We think that, highly uniform 3-5 quantum well nanowire have a lot of potential applications for highly integrated optoelectronic photonic systems. But it's very important to understand some basic, fundamental growth, structure, optical, electrical properties, and thereby we can design device for different applications. Thank you very much for your attention. Well, finally, I just want to promote a little bit the journal that I've been in the editorial board, which is called Optoelectronics Advances. So if you actually work in optoelectronics, please do consider submit to this, quite good journal, which impact factor about 9.6. Thank you very much.
Thank you, ma'am. Now the session is open for questions. Will you spare for 5 minutes, ma'am? Will you be there for 5 minutes?
Thanks,
Hello?
Professor. It's a very interesting session to know about all the works on this optoelectronics, and I hope this is very inspiring for this undergraduates to take up their research in the nano. Thanks.
Yes.
Thanks.
Yes.
Yeah, thank you.
Ma'am, now the session is open for questions. If you have any questions, you can ask now.
Yeah, I guess maybe. Yeah, please go ahead.
Yes, ma'am. Do you have any questions? Ma'am.
I'm very happy to answer very, simple or challenging question, whatever. I think because, it's undergraduate student, maybe it's a little bit, hopefully get a little bit sort of basic understanding of the nanostructure. Yeah. Is someone good?
2 questions.
Yeah.
I'm Vishka from EC branch.
Hi.
I'd like to ask you that you have explained a concept based on nanowire quantum solar cells. Do they create a major impact in vegetation process?
Sorry, I can't hear. You're talking about quantum well solar cells?
Yes. Do they create a major impact on a vegetation process?
For what process? I can't hear. Can you, using etching process, you said, are you asking that question?
Yes. Do they bring a major change or any type of impact or better improvements in farming activities or like vegetation process?
I can't hear very clearly. Can you hear it, Santosh? I can't hear the talk.
Sorry, I'll convey the same thing. Actually, you have explained about LEDs and quantum wells. And she's asking that, is there any impact of those quantum wells in the nano LEDs on the field of farming as well as vegetation process?
Oh, you mean the application for farming and all this?
Yes.
Because we know the LED may be used for planting and tuning the light spectrum to enhance the plant, or is that what you're asking about those questions? Yes. Okay. So it's really, I'm aware that, the visible LED actually, especially the visible LED tuning the spectrum actually have an effect on the growth of the plants. So there's a lot of actually application study on that, but that's visible. I'm not aware of the infrared, because you remember the light I'm talking about is infrared lights. So in particular material I'm working with don't. But for the for the visible light LED based on gallium nitride, materials, they have a lot of active application. They are based on the quantum wells, right? The indium gallium arsenide, the gallium nitride quantum well, they have been widely studied. So they do, yes. But the principle are very similar. Yeah. So you are right. So if you understand some things from what I'm talking about today, you can relate it and translate to other systems as well.
Okay, thank you, ma'am.
Thank you for a very good question. Yeah.
And one more question. One second, ma'am. Yes, ma'am. In present scenario, right from computing to transportation fields require engineered photoelectronic devices or photonic devices and sensors. Thank you for enlightening our budding engineers about 3-5 semiconductors, radial, ring, and axial components in quantum wells, and role of bandgap engineering for photonic devices like infrared LEDs towards emerging technologies, say Li-Fi imaging and optical communication. We are very much impressed with the role of quantum wells and position-dependent photoluminescence model. Actually, myself, K.S. Subramamba, I have completed my PhD and I have some 10 articles related to laser and LED applications, and I have done this position-dependent photoluminescence. But I have the major takeaway from this session for me is current-dependent electroluminescence and selective area epitaxy. I'm very much impressed about the characterization technique model. And here I'm very much impressed about the nano LED arrays which you have done in logos, in developing logos there. I think so it is in 34th slide. Am I right, ma'am? How did you prepare that logo, ma'am? That is ANG logo with the nano LEDs.
Sorry, do you have multiple questions or you have one question mainly about the LED, how we make them?
I'm very much impressed on current-dependent electroluminescence model. And I have one single question. How did you prepare that logo that is ANU?
The logo in the ending. Okay, let me just, because I hear about that, and also you asked about the bias-dependent LED, is it?
Yes.
Yes. So, okay, so there's 2 questions. So bias-dependent electroluminescence, we actually, it's quite interesting because we haven't seen such large sort of shift before from other reports. So we're trying to understand that there could be a few effects there. So there could be when we increase the carrier injection, there might be a shift of the the carrier from the radio versus the actual component. You remember we have these 2 different wavelengths, so there's a shift over there. So combined with some band, what we call band filling effect, because when you inject higher, so some high energy levels could be also populated, leading to the emission. So we are trying to do some simulation to understand that, but that could be due to those effects. Another thing is that when we grow this indium gallium arsenide, indium phosphide, they are not totally lattice matched, but very close to that. But still, maybe we still have some strain inside the system. They could also leading to some effect and also some piezoelectric effect. I'm not totally sure about that. So a few things combined could lead into that the bias-dependent performance. How do we making the logo? Is that we design that with our electron beam lithography system. You actually can design those kind of thing, right? You can really write the patterns and then let the electron beam to actually scan your resist and to define those patterns. So we're actually using electron beam lithography to do that. of course, you always say this could be, you know, very expensive technique, but you can really make it, if you're really interested with different logo or different pattern design, you can always translate that into some, you know, nano imprint system so that would reduce the cost. But that's how we make it. We use the electron beam lithography.
Yes, ma'am. Thank you, ma'am.
Thank you.
Yep. And wonderful session. Once.
Hello, madam. This is Dr. Sedu. I have sent you the invitation, and thank you for acceptance, sir. So I work in the field of ferroelectric-based memory devices and actuators. And just to beside your room, my friend is there. He's Dr. Narayana. He and me are actually colleagues in my post at IEEE in India.
Yeah.
Very awesome. Interesting pattern there. Yeah, but thank you very much for your wonderful session on Nanowires. Yeah.
Thank you very much for very kind invitation. Thank you.
Thank Dr. Santosh sir for giving this opportunity to our students to explore the latest cutting-edge technologies in the nanosensor technology, especially in quantum lights and quantum lattice. Thank you, sir.
Thanks, Dr. Dharma. Thanks, Professor Dan. We understand that it's very late evening for you, but sorry for that. Yeah. So,
no, it's a pleasure. It's great to meet
Thank
you all, and also to see you again, Santosh.
Sure.
Hopefully we can meet in person in the future.
Yes, sure, Professor. Looking forward. Thank you.
Okay, all right. So thank you very much. Good luck with rest of your activities. I'm pretty sure you all will enjoy lots of nice talks over there. All right. Thank you very much. Then with that, I will see you then. Bye-bye.
I request Dr. Registration Master to come on the stage.
For 2 minutes.
Now we are going to have another technical session by Dr. Kirasi. Before that, I request Dr. Registration Master to introduce Dr. Rashi to the projects and processes.
Okay, thank you, sir. So welcome to the second session, I think second talk.
So just
Yeah, students are requesting for 3 minutes break. You can come quickly after 3 minutes. If I see anybody outside, I will continue your attendance for 3 more days.
So, madam,